This talk is about a joint work by Anindya Day, Elkan and Mossel, and myself, Joe Neiman, called Robust Testing of Low-Dimensional Functions. Suppose you have a Boolean function f defined on a very high-dimensional space, but you suspect that most of the dimensions are irrelevant. To what extent can you check that this is really the case? But let's start with a problem that is older and better known. A Boolean function on the discrete cube is called a k-junta if it can be written as a function of just k coordinates. A junta tester is an algorithm that gets oracle access to f, meaning that it can query f of x for arbitrary x in the discrete cube, and it gets parameters k, the junta size, and epsilon, a tolerance parameter. And this algorithm must guarantee that if f is a junta, then the algorithm will say yes with probability at least 2/3. And if f is epsilon far from every k-junta, then the algorithm will say no with probability at least 2/3. Here, the meaning of epsilon far is that f is epsilon far from g if they differ on at least epsilon fraction of the discrete cube. If I were to draw a picture of it, the algorithm would be required to say yes on the set of juntas, and no far away from the set of juntas. There are no restrictions on what the algorithm needs to do when f isn't a junta but is epsilon close to 1. The idea here is that because you only have access to queries, you need to allow some slack to account for the fact that there will be a decent chunk of the inputs that you just never see. The quality of a junta tester is typically measured by its query complexity, the number of queries to the function that you need to evaluate. To gloss very quickly over many works over many years, testing k-juntas with tolerance epsilon takes about k over epsilon queries. Getting the optimal dependence on k and epsilon is nice and all, but really the important thing here is that there is no n. The query complexity is independent of the ambient dimension. Let me mention very briefly that various other considerations have been considered, such as the difference between adaptive and non-adaptive queries, and also some very nice recent work on distribution-free testing, which is when you want to be more flexible in the notion of epsilon far. So that's all about functions on the discrete cube, but we want to study junta-like functions over Euclidean space instead of the discrete cube. Now, we could just copy over the definition of juntas from the discrete setting, but the issue is that in Rn, the choice of basis is often unimportant. So here's what we came up with instead. A Boolean function on Rn is a linear k-junta if it can be seen as a function on some k-dimensional subspace not necessarily coordinate aligned. Another way to write the same thing is, we say that f is a linear k-junta if there is a k-dimensional subspace E and a Boolean function g on E such that f of x is g composed with a projection onto E. Unfortunately, the only kind of linear juntas that I can draw are one juntas in 2 dimensions, but they look something like this. There is one direction here, and the function only depends on the position of the point in that direction. In a previous work, we studied the testing problem for linear k-juntas. So we want an algorithm that gets a parameter k, a parameter epsilon, and oracle access to a function f. And we want the algorithm to return yes with probability 2/3 if f is a linear k-junta, and no with probability 2/3 if f is epsilon far from all linear k-juntas, where here we measure epsilon far with respect to the Gaussian measure, just because it's the nicest finite measure on Rn that I know of. It would be interesting, I think, to consider other measures in the future. Now, unfortunately, this turns out to be impossible. There is no such algorithm. The issue is that, unlike functions on a discrete space, even linear 1 juntas can be pretty nasty. You can cook up a linear 1 junta so that queries to it look basically like random output. The fix is to constrain the complexity of a function. Without getting too much into the weeds, we use the notion of Gaussian surface area as a measure of complexity. It's come up in learning and testing before, and the goal now is to test the class of linear k-juntas that have a bound on the complexity, say, that have Gaussian surface area at most s. This rules out crazy examples like this one, and our previous result was that you can do this testing in poly k s over epsilon queries. The polynomial that we get is unlikely to be optimal, but the point is that there is no n. There is no dependence on the ambient dimension. That was our previous work, and the result was fine and all, but it misses the mark for some potential applications. For example, say that your function f comes from some data, like it's the output of a learning algorithm, and you're trying to do like model compression or feature selection or something like that. You want to get rid of the irrelevant dimensions. Now, you don't expect your function to be exactly a linear k-junta. There will always be some error, and you can't necessarily send it to 0. This motivates the notion of tolerant testing. A tolerant junta tester is an algorithm that gets parameters k, the size of the junta. It gets 2 tolerance parameters, cu and cl, and the algorithm is supposed to return yes with probability at least 2/3 if the distance of your function from the class of linear k-juntas is at most cl, and no with probability 2/3 if the distance of your function from the class of linear k-juntas is at least cu. Cu has to be bigger than cl, u stands for upper, l stands for lower. In pictures, it looks like this. We return yes on some given neighborhood of the linear juntas and no outside of a larger neighborhood. If we're able to do this for all cu and cl, it's essentially equivalent to estimating the distance of f from the class of linear k-junta. And as before, we have to stick in a complexity parameter to make this a feasible problem. And let me also point out that if you take CL to be 0 and CU to be epsilon, then this is just the same as the non-tolerant Junta testing problem that I was talking about before. Tolerant testing has been studied before, both in Junta testing and in other contexts, and it tends to be much harder than non-tolerant testing, both in terms of the query complexity of the known algorithms and in terms of how tight the known results are. It's a bit like how moving to agnostic learning can make things much harder. To explain more the difference between tolerant and non-tolerant testing, let me tell you what's known for the case of testing juntas on the discrete cube. Until recently, there were a few works giving tolerant testing algorithms, but with gaps between CL and CU. For example, Blaise et al. Gave a tolerant tester that works if CU is at least 16 times CL. If you think of tolerant testing in terms of estimating the distance to k-juntas, this is like giving an algorithm for estimating the distance to within a multiplicative factor of 16. With Anindya and Elchanan, we recently gave a tolerant tester that works for every CL and CU, but its query complexity was something like 2 to the k times poly k over epsilon, and the exponential dependence of k was also present in previous works. So that's what I meant when I said that the known algorithms for tolerant testing are worse than those for non-tolerant testing. On the other hand, we have no idea whether this exponential dependence on k is necessary. The best known lower bound is order of k squared, and that's what I meant when I said that the known results for tolerant testing aren't very tight. But anyway, the main result in this work is a tolerant tester for linear k-juntas with query complexity k to the polynomial s over cu minus cl. We don't know how sharp this is, and as you can see, it's much worse than the non-tolerant case, but nevertheless, it's independent of n. We're able to do a little bit more than just testing and actually extract some information about how f can be written as a lower dimensional function. Now, we definitely can't find e with fewer than order n queries, because even specifying a single direction takes order n bits of information. In particular, it's impossible to find the best linear k-junta. However, it turns out that we can find the junta modulo the subspace. In this number of queries, we can find a function g on our k, such that there exists, but we don't find it, a linear map from Rn to Rk, for which the composition is almost as close to f as the best linear k-junta. In particular, this also means that we can test subclasses of linear juntas, like we can test how close f is to the set of XORs of k half spaces or something like that. This is interesting because even tolerant testing for a single half space wasn't previously known. And there's one idea in particular that might be of independent interest, which is the idea of implicit access to the interesting directions. It isn't too hard to see that there is a subspace E of dimension polynomial in k over epsilon that essentially contains all of the potentially relevant linear k-juntas. So at a very high level, the idea of the proof is to first find the subspace, and then to brute force search over all k-juntas contained in it, which we can do because the dimension of the subspace is independent of n. I can even tell you what this subspace E is. After you first smooth f a little bit to make it differentiable, you take the covariance matrix of the gradient, you do an SVD, and you take the top polynomial in k over epsilon components. The intuition is that the gradient of f is a direction along which f varies, and you're trying to choose the most significant ones, so you're doing some sort of PCA on the significant direction. Now, the problem with this is that we can't even write down this matrix. It's an n by n matrix, and so we can't write it down without an n-dependent number of queries. Now, the way we work around this issue is the main idea in this work, which, as I said before, might be useful in other contexts. So we don't write down the interesting directions, because we can't, but we construct oracles to them, or queries to them. More precisely, there is some orthonormal basis, W1 through Wm, of this interesting subspace E, where m, remember, is the dimension of E. We don't write down these vectors, but we do some pre-processing that allows us to query inner products for some arbitrary v in Rn. I'll say the same thing in a different way because I think it is the main takeaway of this talk. There is some mysterious subspace E of dimension m, which is poly in k over epsilon. And although we cannot write down a basis for this subspace in Rn, we are able to nevertheless navigate it using some sort of implicit coordinate system that we have oracle access or query access to. Once we have this implicit access, we can use brute force to iterate over all interesting linear k-juntas in Rn by first brute forcing a discretization of all linear k-juntas in Rm, where m, which is poly k over epsilon, is the dimension of the subspace E. And then, for each of those juntas, putting it in the correct position in Rn by composing it with our interesting coordinates. Now, even though I don't explicitly know the subspace E, I can still query these juntas that we've constructed because I can query each of these inner products. And what that means is that for each of these juntas that I've constructed, we can use queries to measure the distance of them to f and pick the closest one. Now, before I get into any actual details, let me tell you very roughly how we construct this implicit access to coordinates. So imagine that we sample a bunch of points, x1 through xn, in Rn, and we stack up the gradients of f, which remember we smooth so that it has a gradient, in a matrix B. Now, B transpose is an estimate for the covariance matrix that I wrote above, because the covariance matrix is an expectation, and this matrix is an empirical average. Now, remember, I can't write this down because it's n by n. Now, it turns out that we can write down the matrix B transpose B, which is only an m by m matrix. I'll describe a little bit in a little bit more detail later exactly how we do it, but for now, just note that the entries of this matrix are inner products of gradients of f evaluated at different points. So for now, let me describe how to do something easier, which is how to estimate the inner product of the gradient of f with a fixed vector v in Rn. And now this is easy because it's just you can estimate it using a finite difference. The way we do the inner products between gradients at different points is a little bit more complicated, and it has something to do with the way that we smooth the function. So I'll talk about that later. But anyway, once we've written down this matrix, then the vectors w1 through wm that I'm looking for are the rows of the matrix B transpose B to the minus a half times B transpose. So these rows are orthonormal just by linear algebra, and they also span the same space as the rows of B transpose. And while I can't write down this matrix because it's m by n, I can query it at points in Rn, because I write down this matrix, which is m by m, and I query these inner products. Now, I realize that the outline that I just gave is probably quite cryptic, and so what I want to do next is go back and give a few more details and explain things a little bit better. Let me start with the notion of smoothness that we're going to use. And in particular, we're going to smooth functions by applying what's known as the Ornstein-Uhlenbeck operator, or the Gaussian noise operator. It's defined like this. So to evaluate the smoothed function at a point, I am taking a Gaussian average over the values of the original function. Now, we won't be too concerned with the exact properties of this operator, but there are two things that will be important to us. So the first one is that it makes any function smooth, and not only smooth, but with a bound on the gradient. So Lipschitz, in other words. And the second thing is that, and this is where the notion of complexity in Gaussian surface area comes from, that if you start with a function of bounded Gaussian surface area and you smooth it, then it's not changed too much. And let me point out one more final thing about this noise operator, which is that if we have query access to f, then we can simulate approximate query access to the smoothed f, simply by replacing this Gaussian integral with points sampled from a Gaussian measure. So now the idea is just, I take t small enough so that this term is negligible compared to the tolerances I'm interested in, and then for the rest of the argument, I'm going to work with a smooth function. Let me tell you a little bit more now about the subspace E that we'll be finding. The idea is, I look at this, the covariance matrix of the gradient of my smooth function, and I claim that if I take the span of the eigenvectors of this matrix corresponding to not too small eigenvalues, then I get a subspace with the property that the best Hunter correlation among all functions in Rn is close to the best Hunter correlation among functions that live only in this subspace. Our main tool for showing this is the Gaussian Poincare inequality, which says that for any function on a Gaussian space, the variance of the function is bounded by the squared L2 norm of the gradient. And so at a very high level, what's going on is that the directions which are orthogonal to my subspace here don't contribute much to the L2 norm squared of the gradient. And so if you apply the Gaussian Poincare inequality just in those directions, you conclude that the function f can't vary very much in those directions. In particular, what that means is that if I take a k-Hunter, which is defined on some other subspace, and I compare its distance to f against the k-Hunter obtained by averaging my original k-Hunter on the subspace E, then they're almost the same. And this means that the best possible Hunter in all of Rn is not much better than the one that I get from averaging that one on E, which is a Hunter defined on E. Now, all of this, of course, was for the subspace E, which was defined by doing SVD on an expectation, but it's not too hard to show using some basic random matrix theory that I can replace this by the empirical version that I mentioned before. So that's the interesting subspace, and next I should tell you how to estimate the inner products of gradients at different points, which is how you are able to write down this matrix that I call B transpose B. This is very closely related to how we do our smoothing, and it basically follows from two tricks and a bunch of algebra. I'm just going to tell you the tricks, and you can see the paper if you want to see the algebra. So the first trick is that integrating by parts against the Gaussian density, you get that the expectation of the gradient of any function is the same as the expectation of x times that function. This thing on the right-hand side is sometimes called the level 1 coefficients of f because it's the degree 1 part of the Hermite expansion of f, which is the Gaussian analog of the Fourier expansion on the discrete cube. This is relevant to our problem because the gradient of the smoothed function can be expressed as the expectation of a gradient like this. So it's the expected gradient of a shifted and scaled version of the original function. Anyway, the point here is that this inner product of gradients is like the inner product of the level 1 coefficients of these shifted and scaled functions. Now the second trick is that we can extract the level 1 coefficients by applying the noise operator. When you apply noise, you magnify the effect of the level 1 coefficients compared to the higher level 1. And so you can estimate this inner product of level 1 coefficients by estimating this expectation, which is something that you can do with a small number of queries. I should point out that previously we applied a little bit of noise just to get some smoothing. This time we're applying lots of noise to extract the level 1 coefficients. Okay, so now we have a way to estimate these inner products, and so we have a way to estimate the matrix B transpose B. Let me remind you how we put all these things together, partly because I lied a little bit in the high-level overview before. I'm interested in the span of the eigenvectors of this matrix, which have non-tiny eigenvalues. And I get an orthonormal basis for that space by taking the rows of this matrix product, where by this notation here, I mean a sort of truncated pseudo-inverse, where I only consider the non-negligible eigenvalue. And let me remind you that in writing down this matrix product, this part here is something that we have computed. And this part here we can't write down, but we can estimate the product against arbitrary vectors. And so I can estimate this whole product for arbitrary vectors in Rn. If you think much about numerical stability, you might be worried about this operation because it's very unstable. You need an extremely good estimate for the matrix B transpose B before you can get a good estimate for the truncated pseudo-inverse, especially if you don't know that there's an eigengap or something like that. What saves us here is that we're actually still happy if the subspace E that we get is too large. It's okay to include some irrelevant directions, as long as we don't have too many of them, and we also have all the important ones. So what we do here is we take the threshold to be much smaller than we actually need. And what that means is that the numerical instability of this pseudo-inverse operation is mainly restricted to the eigenspaces that we don't care about. The eigenspaces that we do care about are actually quite stable. The very final thing is the brute force construction of all the linear K-juntas in Rm. Let me remind you where this fits into the big picture first, maybe. Now that we have this matrix, which allows us to implicitly access the interesting directions, we consider all the possible K-juntas in Rm, and we position them in Rn like this, and then we're going to iterate over them and estimate their distance to the function f. So the first thing that we do to enumerate all of the linear K-juntas in Rm is we find the set of k-dimensional subspaces in Rm, and we find a very fine discretization of it. There are about k over epsilon to the power mk of them, and remember that m, which is the dimension of E, is poly k over epsilon. Then we enumerate over all functions with Gaussian surface area at most s on Rk. There are about e to the k to the s squared over epsilon squared of them. This has been known for a while. And for each of these K-juntas and for each of these subspaces, we get a linear K-junta in Rn, like this. Then we estimate the distance of this linear junta to our function f just by sampling some points. And we repeat for every function in our discretization. Now there are a lot of functions here, which means that the running time of our algorithm is huge, but the query complexity isn't too bad, because although we need to query f a bunch of times to compute these inner products, we can then just reuse the same inner products for the other junta candidates. And the number of samples that we need here to get a good estimate for every candidate junta in our discretization is, by standard Chernoff bounds, just the log of the number of candidate functions. And that's where our query complexity comes from, the log of the exponential of k to the s squared over epsilon squared. So that's the main idea behind our testing algorithm. Let me just write it down for you once, just so you can see the whole thing in one slide. And finally, let me recap for you the main result, which is that a linear K-junta is a function which depends only on some k-dimensional subspace. Our main result is that we can tolerantly test the class of linear K-juntas of bounded Gaussian surface area, which is the same as saying we can estimate, using queries, the distance from a function to this class. And our main tool is that we construct this kind of oracle access to the interesting subspace with a query complexity that is independent of the underlying dimension n and depends only on the Hünte size k and the tolerance parameter epsilon. That's all, and thanks for listening.